and we're going to talk about something new today. It's similar to something that we talked about before, but it is a new topic. So this is 10.3. Here's our objective. Here's our goal for the day. We want to make sure that we understand and can use the triangle proportionality theorem. So write the word theorem, and its converse. Can somebody remind us what a converse of a theorem is? We've talked about it a few times. You talked about it last year. Yeah. It's when we go backwards. So when we have the hypothesis, the if part, and the conclusion, the then part. Okay, that's the theorem. And if we can switch those, that's its converse. Okay, and we talked a little bit about yesterday saying if and only if and stuff like that. Those things with parallelograms, they worked both ways. Okay, and that's kind of what we're talking about here. This triangle proportionality theorem is going to work forwards and it's going to work backwards. So on a problem like this, pretty darn easy. I multiply those two together, so I get 15. I multiply on the other side, I get 4x plus 24. I start moving stuff around and I solve this. So I'm going to subtract the 24. I get I got a negative 9 equals 4x. And divide by 4. I end up with x equals negative 9/4. Okay? No surprises. We've been using proportions for quite a while, right? We're going to be using more proportions today, and some of them are going to get a little bit weird. It's the setup. It's not going to be the solve part that's very difficult. Okay, take a look at the next one. It says BD is a mid-segment. Can somebody raise their hand and remind us, what is a mid-segment? They tried to name it something that reminds you what it is. Keely? It does kind of cut the triangle in half. What does it connect? What are the endpoints? Yeah. Those are midpoints, okay? So if these are midpoints, if that's a mid-segment, it cuts this in half. So if this is 4, that's going to be 4. If this is 5, that's going to be 5. Okay, that's one helpful thing. And the whole half part that Keely was mentioning, because we still got a piece that we're missing. D?
The mid-segment is half of what the A and E is at the bottom.
Very good. So the mid-segment is exactly half of this other side over here. So this is going to be 12. And then we also know that those two would be parallel. Those lines would be parallel. Okay? Any questions there?
No.
There's our question right here. We know that BD and AE are parallel. So I'd like to do one thing in the warm-up that I think will help as we do the assignment today. I remember learning about this in high school in Mr. Hong's geometry class. We were looking at this, and it took me a while to go, oh, that's how it works. I mentioned this before. Sometimes when you have a diagram with overlapping things or things that are not oriented the same way, it can be helpful to kind of decouple those or rotate them and different things like that. So here's what I'm going to do. I'm going to draw the small triangle right here, and I'm going to draw the big triangle right here. We've already got the measurements in the corners. So this is CBD, and this is 4, 5, and that's 6. And if I draw the big one, this is CAE, and the measurements would be, well, that entire side got cut in half, so the whole thing is 8. This entire side got cut in half, so this one's 10. And this one over here is 12. So now you can look at it and you can kind of tell, hey, there's something kind of cool about these. These are similar triangles because they're all in the same proportion. And in fact, from this, you can figure out the constant of proportionality if you want to be fancy about it, or the scale factor. So take a look at this one. How much bigger is this one? Si?
2.
It's 2 times bigger. Or looking at it the other way, the small one is half the size of the big one. Okay? So earlier in the unit, this is what we learned about. We learned about the triangle mid-segment theorem. It creates that parallel segment and it divides the triangle proportionally. It's this very picture, this very idea up here that we've been talking about. Well, it actually turns out we can kind of extend that idea so it can be used on other segments that divide the triangle as long as the segment is parallel, and this is the key, it's got to be parallel to a side. Okay? So this is the triangle proportionality theorem, and we'll do its converse in just a second. So if a line is parallel to one side of the triangle, then it divides the other two sides proportionally. So if this is parallel to this little dividing line right here that goes from B to D, if those are parallel, then what it means is this segment right here, and I'm not going to put a slash through it, it's got to be proportional to this segment right here. And this segment right here is proportional to that segment right there. So you can imagine taking that and sliding it closer in that little tiny piece on the bottom. These would get really small and that one would get really big, or vice versa, sliding it way up here. Okay, they're still proportional to each other. So here's what it means as far as the pieces go. We're literally talking about the pieces of the side that got divided. So if BD is parallel to AE, then what we can say is CB, which looks like a big piece right here, is proportional to BA. So if I set up a ratio of CB to BA, it's got to be proportional to the same type of thing on this one. So I'm doing this to this, so I'm going to do this to this. So that's going to be CD to DE. And its converse would be this. If a line intersects intersects two sides of a triangle and divides them proportionally, then it's parallel to that other side, the third side of the triangle. So on the diagram to the right, this is what it would mean. It would mean if those end up being proportional, so it's the same proportion that we wrote here, CB to BA, this piece up here to this little piece right here, if it's proportional to that piece right there, so CD to DE, then we know for a fact that BD is parallel to AE. Works both ways. So if it's parallel, it chops those other sides proportionally. If those other sides have been chopped up proportionally, then we know those are going to be parallel. Okay, so that's the converse. It works both ways. Okay, now I want to slide down here, and this is what's worth noting. The theorem only talks about the pieces, but I want you to notice something. If those are parallel, I've got a small triangle here, and I've got a big triangle here. And this is CBD, and this is CAE. And those triangles, if you take a good look at them, because they share that vertex angle, and these are parallel. And take a look at angle 1 and take a look at angle 3. What do you know about angle 1 and angle 3? They're congruent because they are corresponding. They're corresponding angles. This is the transversal that comes down and cuts across those two parallel lines. So we would have angle-angle similarity. So those two triangles are similar. And if those two triangles are similar, then we've got a whole bunch of stuff that we can write down. We can write down that CB is similar or in the same ratio to, let's see, so if we do CB to CA, CD to, that would be CE, and AE's on the bottom there, what goes on the top would be BD. So now I want to come back and take a look at this diagram and show you what we can use. Oops, let me leave these. Okay. So not only are the pieces proportional to each other, these big sides out here would have to be proportional to each other because they would be those corresponding sides of these triangles that we just drew here. Okay? So we can use pieces to the entire side and use that proportion. So there's a bunch of different ways that we can solve many of the problems. Some of them there might be only one way, but there's a couple different ways that we can solve those. Okay, so everybody see that little consequence there. The theorem just talks about these two little segments being proportional. The consequence of that is, hey gosh, actually I can match up all of these sides of those two triangles and they would be proportional. Okay, any questions? All right. So if you messed around a little bit, you might even be able to find some other things that are proportional in this, but we're going to take a look at this one right here. So it says solve for x and y, and it says these are similar. Okay, so it actually goes to the trouble of telling us they're similar, even though we could figure out that they're similar just by statement here. So let's find x. So x is a piece. So let's match up this side with this side and this side with this side. Or I should say this piece with this piece and that piece with that piece. So I'm going to do x over 32. If I do x over 32, so if I'm doing this piece to this piece, Then I need to do this piece to this piece. So that's going to be 10 over 30. Now, if you want to, a couple quick things that I want you to notice. This is a very simple proportion to solve. I put the x on the top, so I don't have to, it's already up where I need to solve for it. Okay. The other thing you'll notice is, and this doesn't happen all the time, but if you do get something with bigger numbers, if you want to reduce that to 1/3, that's totally okay. If you want to leave it 10 over 30, that's fine, and then simplify after the fact. But I'm going to go ahead and cancel those off. So that means the only thing I need to do to solve for x is multiply by 32. So I'm going to get x equals 32 over 3. I'm going to put a box around that, and I'm set to go. So this piece right here is 32 over 3. Not the nicest answer, but it'll work. Okay, any questions there? That's a direct use of the theorem. The pieces are proportional to each other. Okay, here's the next one. We got to find y. The tough thing about y is not one of those pieces. Y is this piece here, and we could compare it to that piece right there. So it's a side on the small triangle and a side on the big triangle. So here's what I'm going to match it up with. I'm going to match it up with that side on the small triangle and this side on that one. So I'm doing the piece to the entire side, or this entire side to that entire side. So I'm going to do 30 over 40, because that's how long the whole thing would be, right? Let's see, if I did 30 to 40, if I did the small piece to the big piece, small piece to the big piece. So this would be y over 22. Any questions? Cancel those off. Times by 22. Do a little bit of cross cancellation here. So this would go in twice. That would go in 11 times. So this is going to be 33 over 2 equals y. And there's my answer for y. Not the nicest numbers, but it works, doesn't it? Okay, any questions? Again, if you have any trouble, you can always take those overlapping triangles and make them so they're not overlapping, and then solve it that way. So if I take a look at this one right here, some people would be tempted to say, hey, if this is 3, that's going to be 3. Is that the way it works?
No.
It's not. Okay, so we're going to do 4 to 5. I'm going to do this piece to this piece. So if I do the piece on the top to the piece on the bottom, I'm going to do the 3 to the x. And then I'll solve that. Again, if you want to do it this way, that's totally okay. There's no problem. I end up with, that's a 15. Divide by 4. So I get x equals 15 over 4. Yeah.
So you can take the difference of the larger sides instead of just their combined total?
Where did I take the difference of the larger sides?
Well, you're just using 5 and x and not 3 plus x and 9.
Yeah, because all I'm doing is doing this one. I'm going to do the full sides in just a second to find the other one. Okay. So let me see if we can get there. I'm going to change colors for the other part because this is a full side on the triangle. So what I need to do is I need to know that, hey, this is 9. I mean, if I wanted to, I could write down that this is 3 plus x, which is 3 plus 15 fourths. I mean, I could do this, but this is going to be a fraction. So it's probably going to be a lot easier for me to do something like this. I'm going to compare 4 to 12. And if I compare 4 to 12 on the small triangle, I'm going to compare this side right here, which is 9, to that side on the big triangle. So take a look at it. We've got these overlapping triangles. I'm doing this side on the small one, comparing it to this side on the big one, so 4 to 9. And I'm comparing this side on the small one to this corresponding side on the big one, so that one's going to be, I wrote that down wrong, didn't I? Oh, no, I didn't. Okay. I think what I just said is do 4 to 9 and do 12 to y.
That's what it should be.
Okay. So here's the cool thing. Okay, and this gets to what's on the next page. If you set it up this way and your friend set it up that way, are you both going to get the same answer?
Yes.
Yeah, because all you did is you chose to flip them over. You could even change sides and stuff like that. You're still going to get exactly the same answer. So if we multiply the two of these, so I'm going to end up with 4y equals 12 times 9. I'm going to divide both sides by 4. So this is going to be a y equals, that's going to be a 3. Did you get 27?
Uh-huh.
We good there? Okay, flip the page over. Okay, so this came up already. So there's a little asterisk right here. There is often more than one way to solve these. So you can solve it a really complicated way if you want to. You can solve it a really easy way if you want to. As long as you're getting the correct answer, you don't need to argue with your friend about what's the best way to do it. It's what makes sense to you, that's valid and true, and would work every single time. So on this one, you'll notice what we've got here is these are parallel. If those are parallel, then we know that these pieces are proportional. So I'm going to set up 6 to 18. And if I set up 6 to 18, I've got to do the corresponding thing on the other one. I've got to do x plus 2 to x plus 22. Now, if your neighbor happened to flip those over or do something like that, would that be okay?
Yes.
Totally okay. I'm probably going to reduce. Are you going to reduce? Yeah, this is 1/3. Okay, so this is going to give us x plus 22, 3x plus 6. So I got 16 and 2x. Did you get x equals 8?
Yep.
Okay. All right, so we're good there? Okay. I just want to check something. What if your neighbor did this? I'm going to change colors. Don't write this down. What if your neighbor said, hey, I'm going to compare these two to each other. So I'm going to compare x plus 22 to 18. And I'm going to compare, let's see, if I do x plus 22, I'd have to do x plus 2 to 6.
Doesn't matter.
Does it work out?
Yes.
Would we have ended up doing the same thing? Works out, doesn't it? Okay. All right, let's take a look at this one right here. Okay, this one is one of those where, because we're just trying to find this one thing right here, there's probably one best way to do it. You might be able to find another one. But for this one, we need one more piece of information because this side right here is on the big triangle. So we have to know a length to compare to. Any ideas?
20.
This side out here is 20. Okay. Would you go ahead and set one up you think will work for this? Mason?
So I'm still not quite understanding how you can just like on A, how you can just take 6 and 18 and not combine them. Like, because right, the triangles are proportional, but you're like taking the proportionality of the trapezoid.
Okay, so let me answer it this way. You could, and I'll come back and do it a more complicated way. This would be 24, and then you would want to compare this to 2x plus 24, right? You could do that, it will give you the same answer. Okay, so we'll come back and show you in a second. Okay, hang on. Okay, raise your hand if you did exactly what I wrote down. Interesting. Okay, if I multiply the two of those, and I'm not going to simplify it on this one, if I multiply here and here, do the cross multiplication like I normally do, if you reduced it or whatever, do you end up with that equivalent? Okay, so this is still going to be, this would be a 20x plus 60. This would be a 24x. I'm going to move the 20 to the other side, so that's going to be minus 20x. So I'm going to end up with, let's see, this is going to be 4x equals 60. So I got x equals 15.
Yes.
Raise your hand if you got that. Okay. You may have set it up a different way, but it still ended up with being x equals 15. If you're interested in Mason's question, stick around for a bit. Okay, come down here. Let's take a look at these guys. This one is a different question. Notice what it asks us to do. Determine whether those are parallel. And here's what it says. HM is 15. So that's 15. HN is 10. So this is 10. So we can figure out that this is 5. Not too bad. But then it says this. HJ, so this piece right here, is twice the length of JK, and you don't know what either one of them are. Jack? Go ahead.
You could say 2x next.
Yeah, if this one's twice as big as that one, say, I don't know what that one is, but I do know that this one's twice as big. And then all we need to do according to the theorem is show if those are proportional, then they've got to be parallel. So if I take 10 and put it over 5, I'd have to put 2x over x, and this simplifies to 2, and that simplifies to 2, which means they're in the same proportion. They are proportional to each other. So I'm going to put these 3 dots, and I'm just going to say, therefore, NJ is parallel to MK. So you've got some problems that are not necessarily arithmetic or algebra problems. They're just, hey, can you just verify that this is actually the case, like we were talking about the other day? Okay, any questions? Okay, last one. It says find the length of every one of these. So we want to do TO, that's going to be what X is. OR, that's going to be what Y is. And then we want SP, so that's this one over here, and RP, that's this one right here. So basically these 4 little side lengths right there. Okay? Any ideas? Luke?
No.
Wilson?
You could do like 9 over x plus 5.
Okay. So he's comparing 9 to x plus 5, and what would the other one have to be?
6 over x.
6 to x. Very good. So I'm going to do 6 to x. D, will you grab the door back there? And then 9 to x plus 5. So I probably do need to figure that out first. Let's go ahead and figure that out. So this is going to be 9x, 6x plus 30 when I multiply here and multiply there. Subtract the 6x. Got x equals 10? Okay. So this piece right here is 10. I'll go ahead and mark that. This is 10, so that one's 15. Now I can do the next one. Okay, I'm going to change colors. Somebody want to set up the next one for me? There's more than one way to do this. Anybody want to give it a shot so we can solve for these y's here? Yeah.
Would it be x plus 5 over 9 is equal to plus 8 over 9? So you would do.
Yes, but we know what this one is, so we don't need x plus 8.
So
Yeah, so we're going to do 15 over 9 is exactly the same. So if we're doing 15 over 9, we're comparing this piece to this piece. Okay, that's what we're doing. So this would be y plus 8 over y. I'm going to reduce this. This is 5/3. Everybody okay with that? So we're going to multiply here, 5y, 3y plus 24. Ooh, luckily this works out nicely, right? 2y equals 24, so y equals 12. Got a nice number? Okay, so that piece is 12 and that piece is 20. Everybody good? Okay, so TO is 10. SP is this one right here, that's 15. OR is this one right here, it's 12. And RP is this one right here, that's 20. Would you fill out the I can checklist right there? Rate how you're feeling. And then if you're interested, you can stick around and Mason is going to ask and we're going to talk about why on earth can you just chop those up like that? Why don't you have to compare it to the entire side? And am I summarizing your question?